Hello, everyone. Welcome back to the AAS YouTube channel, and this is part of the good stuff. This is the AAS Journal Author Series, and I'm very happy to have Bruce Draine and Brandon Hensley with us today. Hello, Bruce. Hello, Brandon.
Hi, Frank.
Hello, thanks for having us.
Oh, yeah. Well, thank you so much for being willing to talk about your really lovely APJ paper here, which we'll get to soon enough. And where are you two located?
Well, I'm in Princeton, a few miles away from Princeton University, but working at home today.
You have an awesome home office there. It almost looks like a real office with, all kinds of books and bookcases. And
I spend a lot of time here.
what is that? What is it? You have like a white, is that a copy machine off to the left, that white one?
Oh, no, well, yeah, actually it is. It's an inkjet printer.
Ah, okay, very good. All right. And Brandon, where are you located at?
Yeah, so I'm a Spitzer postdoctoral fellow at Princeton, but I've actually been working remotely from Huntington, West Virginia for a while.
Okay, so that's where you're at now? You're at West
That's where I'm calling in from right now.
Very good. Is there snow on the ground yet in Princeton?
Nope, afraid not. We had flurries yesterday, but nothing stuck.
Okay. How about West Virginia? What's your altitude there, wherever?
Yeah, no, I'm on the very western tip of West Virginia, so out of the main mountains. But we did get a dusting this week.
Oh,
it was gone by midday, but it was a little bit in the morning.
Cool. It is December 10th, 2021 is we record this one. So very good. Brandon, what do you like to do for research?
So a lot of my research focuses on interstellar dust and what dust is, what it's made out of, size, shape, optical properties. And so I think really what I like to dig into is making the connection between detailed theory and observations.
Nice.
Another branch of what I do is I'm really involved in the cosmic microwave background community, thinking about how to both model dust polarization so we can get rid of it to get at our great cosmological signals, but also to think about all this great microwave polarimetry data that's coming in and how we can use it to learn about dust and the Milky Way.
Nice, very nice. And Bruce, what do you like to do for research?
Well, I'm a physicist, and I got interested in all the things that go on in the interstellar medium, and I considered it a great sandbox to play in. But I find myself obsessed with interstellar dust and trying to tease out from the clues that nature gives us and the laws of physics what it's likely to be like. So my thesis advisor set me off in that direction, more or less against my will. But once I got into it, I found it so interesting that I can't get myself to stop. So the quest goes on.
Oh, because I'm always curious, because there's so many things to do in astronomy, right? I mean, you could do X, Y, Z, and so I'm always kind of curious how people got into the field that they do. So it sounds like you were a little bit shanghaied there, a little bit recruited. I don't know if the same holds for you, Brandon, or that was a little bit more of a free will choice.
So I came into grad school wanting to do a project on interstellar dust, and so I asked, Bruce, you have any dust projects? And then after the first project, then I was hooked too, and that's how it happened.
Nice. And this is then going to bring us to this very lovely APJ article using the Starlight polarization efficiency integral to constrain shapes and porosities of interstellar grains. And Bruce and Brandon, take us away.
Well, let me try to just start with a big picture of what we're trying to do here. So as we've just been saying, we're trying to figure out what interstellar dust is, and nature has given us a lot of observational information, and we have the laws of physics. We've had measurements of starlight polarization for many decades. It was discovered completely by accident by people who were not looking for starlight polarization by interstellar dust, but it was discovered that interstellar dust polarizes starlight, and that has proven to be a useful and powerful data set in addition to the reddening of light by starlight. Mm-hmm. So we know about that as well. So we try to make models that are compliant with the observations, and that turns out, when you're doing the polarization, is technically a challenging problem because it means you have to calculate the optical properties of non-spherical things, because spheres will not give you starlight polarization.
Right.
So that has limited the amount of progress made in the field, simply because it's technically hard to do. But we're getting better at solving our technical problems. And Brandon and I realized that much of the information about the starlight polarization could actually be collapsed into an integral, namely the integral of the polarization as a function of wavelength over wavelength. Is something which is related to the grain cross-section, the cross-section for producing polarization. And it's an integral property which you could then ask, can I make a grain model which, even aside from whether we're going to reproduce the details of the starlight wavelength dependence, can it reproduce this integral property? And that turns out to be a fruitful way to go because it speeds up our analysis. So we can now explore model space and delineate in the model space what has to be true of models with non-spherical grains if they are to reproduce the observed strength of the starlight polarization, which I should mention, it varies from one direction to another, but we find that in some directions, presumably where we're looking perpendicular to the galactic magnetic field, we get the maximum amount of starlight polarization. So it's really the maximum amount of starlight polarization per reddening that a grain model has to be able to reproduce. So that has been an interesting enterprise. But now, in addition, our science has been enriched by the Planck observations. So Planck, of course, was designed to study the cosmic microwave background. But in a sense, about 50% of Planck's capabilities were actually specifically designed to be sensitive to the polarized emission in the submillimeter by interstellar dust, so that the interstellar dust contamination of the microwave background could best be subtracted.
Right.
And those Planck observations ended up being somewhat shocking to us. So let me just switch to Brandon. Brandon is much closer to all of the observations than I am. So I'd like to let him pick up here.
Okay.
Yes, I'll pick up the story on the Planck observation. So Bruce mentioned that it was really shocking to us. And I think there's really two facets to these Planck observations that really kind of upended the way that we were thinking about interstellar dust models, and that kind of indirectly paved the way for the tack that we take in this paper. So the first thing was that the total level of dust polarization, the dust polarization fraction, was much higher than what was predicted by models. So if we really pushed our pre-Planck dust models hard, we could get them up to maybe 15% polarization fraction in the submillimeter. And Planck was finding regions of the sky where the dust polarization fraction exceeded 20%, which is a huge gap thinking about it from the modeling point of view. So our dust was not creating enough polarization. But then the second thing that was even more devastating to dust models was the fact that if you look at the spectrum of the polarization, it looks more or less exactly the same as the spectrum in the unpolarized radiation. Okay. And so in these classical dust models where you have silicate grains and carbonaceous grains, these two distinct populations, you would expect them to generically have different polarization properties. And so they'll add together, they'll sum differently in total intensity than they would in polarized intensity. And so you just naturally expect the shape of the dust SED to look different in total intensity versus polarized intensity, such that if you took the polarization fraction, the ratio of those two, it should be dependent on the wavelength of light that you're looking at. And what Planck found was a remarkable constancy of this polarization fraction with wavelength, exactly. And this was supplemented by higher frequency observations by the blast pole balloon, not accessing the very diffuse medium, but kind of in the outskirts of molecular clouds, again, finding from 250 microns out to maybe 3 millimeters, sub 10% deviations in this polarization fraction. Okay. And it was just really in conflict with this notion that there's these two grain types running around with different properties.
Okay.
And so what Bruce and I have been putting forward is that this old dichotomy between this carbonaceous grains and the silicate grains may actually not be the case, and that really you have one grain type in the interstellar medium is kind of a mishmash of some domains carbonaceous, some domains silicate, and we refer to that as astrodust.
Mm-hmm.
And one nice thing about that is once you take away this degree of freedom of having these two different dust populations, you can start making very generic, even model independent things by the fact that you only have one population of grains that's responsible for the observed phenomena. Cool. And so we find in this paper that we can make very strong constraints on what the properties of this astrodust has to be able to reproduce what we see in the starlight polarization and in the submillimeter polarization.
Very nice. Very nice.
So I might mention that also from a theoretical and observational standpoint, even though we don't know what dust grains are composed of in terms of their chemical constituents, we do know what the atomic constituents are because we have many years of careful observations of the depletion of elements from interstellar gas. Right. So we know how many atoms of iron and silicon and magnesium, and to some extent carbon, and to some extent oxygen are in the dust grains, along with little bits of other things that don't really matter numerically. So we can say what the total volume of grain or mass of grain material is, even if we admit to being uncertain about exactly what chemical form it's in. And so that volume of grain material is a reasonably robust constraint on any modeling, even though you may not know exactly what kind of grain material you want to envision. So it allows you to our approach is bypassing the specificity of material and only talking about the volume of material, and then asking what the optical properties of the material, this hypothetical astrodust, have to be in order to reproduce the observations, and they should be physically possible optical properties.
Right.
And so one of the observations is the degree of starlight polarization. And so we ask the question, just how non-spherical do the grains have to be if they are perfectly, not all perfectly aligned, but if all the large grains, one thing we know is that the small grains are actually not aligned. Mm-hmm. So without getting into the details of starlight polarization, there's a history of looking for it in the ultraviolet and discovering that starlight polarization is very weak in the ultraviolet, even though extinction is very strong in the ultraviolet. Okay. So nature does not allow the small end of the size distribution to be aligned. But the larger end is manifestly aligned, and it can't be more than 100% aligned. So we can constrain the volume of we can deduce the minimum amount of elongation that the grains have to have, mm-hmm. so that even if the ones that are possibly fully aligned are fully aligned, they would be able to reproduce the starlight polarization. So there's actually a figure in our paper where we could jump to that result of just the starlight polarization constraint. So it would be figure 10 would be a good one to look at here.
Take a look at that. I have a question while I'm scrolling there. Are there any laboratory astrophysics things that one can do? You'd think you'd be able to make suitable sized dust grains and all of that? So it's just sort of a general question. Are there laboratory astrophysics?
Well, there's definitely an active program in laboratory astrophysics, and people try to synthesize materials that could be candidates for interstellar grains, both carbonaceous materials. We know some of the stuff in grains is carbonaceous, and silicate-based materials. We know that a substantial amount of the interstellar grain mass has to be some form of amorphous silicates. But those studies clearly inform us and tell us what kinds of things seem physically reasonable, but it's not been possible to come up with grain materials in the laboratory which provides such a good fit to the observations that we say, aha, this is the stuff that's out there
Right.
for the general properties of the dust component.
Okay.
I mean, it kind of is the ideal, right? To eventually meet in the middle, to have agreement between what we infer from the astronomical observations, kind of the remote sensing approach, and then the laboratory synthesis. But yeah, we're certainly not there yet.
Okay.
So do you want to describe this figure, Brandon?
Go ahead.
Figure 10. Fire away.
Well, okay, so I'll briefly describe it. So based on the constraint of knowing what the volume of grain material is allowed to be by the available elemental abundances that we believe to be removed from the gas and are residing in the solid phase, we can say if we restrict ourselves to spheroidal shapes, so you have to, we're taking baby steps here. We don't imagine that interstellar grains are really spheroids, but we do know that they're not spheres.
Right.
So we have to move beyond spheres, and we have to have a shape which is computationally tractable. And so spheroids is the next step after spheres.
Yep.
And so we can explore the family of spheroids, both prolate, i.e. cigar-shaped spheroids, or oblate, i.e. pancake-shaped spheroids, frisbee-shaped spheroids, if you will, and ask what axial ratios would be large enough so that if 70% of the grains were perfectly aligned, of the grain mass, of the grain volume were perfectly aligned, would we be able to achieve the highest levels of starlight polarization that are observed? And this figure shows that it depends on one additional parameter. You're allowed to envision that the grains, even though you know the total volume of solid material, the grains may be porous.
Yeah.
So porosity has been considered to be a very natural thing to envision for interstellar grains. And so we now allow ourselves to increase the total volume of the grain to be larger than the volume occupied by the solid material by introducing porosity. So we're constraining the volume of the solid material, the mass of the solid material, but now allow the grain to be porous. And an interesting result is that if the grains become porous, they are less effective at producing polarization. So that's something we knew, we expected theoretically, but it hadn't really been explored systematically. And so this figure shows that if you take grains where the porosity is zero, so look at the black curve there, that's zero porosity. So if we're on the oblate side here, then if this dashed line, this region above 70% is shaded red, this is the fractional alignment of the grain material. And as I said, the small grains can't be aligned, otherwise there'd be too much ultraviolet polarization. And we think that more or less the maximum amount of aligned grain mass is about 70%. So we think the region below this 0.7 line is allowed. And the different curves here show for a given porosity how elongated the grains would have to be to reproduce the starlight polarization. So if you look at the point where the black curve intersects this 0.7 line, that says that if the actual ratio is about 1.4, the grains could actually reproduce the starlight polarization if 70% of them were perfectly aligned. But if you go to larger porosities, look the magenta curve there on the right, 0.7, now you can't reproduce the starlight polarization unless the grains are really non-spherical. Axial ratio has to be more than 2 to 1, 2.3 to 1 or something like that. Now we don't know how non-spherical the grains are, but sort of intuitively, I would think axial ratios of 1.5 or 2 are plausible. But if somebody starts telling me they have a model that requires axial ratios to be 3 or 4 or 5, it just seems to me to be less likely to be true, even though we don't know at this point. The other interesting thing is that prolate grains are also less effective at producing polarization. So you have to go to more extreme axial ratios if the grains are prolate. That has to do with how they spin. So we don't have the time to talk about the spinning of the grains, but we are in all cases assuming that grains are spinning, and they're spinning around the axis with the largest moment of inertia. So for oblate grain, that's the symmetry axis. But for a prolate cigar-shaped grain, that's an axis perpendicular to the symmetry axis.
Right.
So I think we're probably spent too much time on this figure. This is just the starlight polarization. We haven't yet introduced the submillimeter. Now, let me just ask Brandon to pick up here and talk about how Planck actually led to new findings about the starlight polarization.
Right. So, okay, we have a characteristic ratio between submillimeter polarization and starlight polarization, as it turns out. Because if you think about it, it's really the same grain population that's giving rise to both of these phenomena, the extinction in the optical and the emission in the submillimeter. And so the Planck collaboration did a very nice correlation study where they took a sample of starlight polarization and correlated that with observations of the polarized emission in those same regions of sky, and found a very linear correlation between the two, as one might expect. And the ratio of that correlation is very interesting and constraining on our models, and we'll talk about that in a second. But the other implication is, well, okay, Planck sees these regions that are polarized at 20% polarization fraction, which was much higher than expected. Well, doesn't that mean that the stars should be polarized extremely highly there too? So if you follow this linear relation and make a prediction as to how polarized these stars should be, these stars should have a polarization per unit dust reddening that exceed the classical envelope that was set down by Sierkowski in the 70s. That's, it seems like this is the maximum amount of stellar polarization per unit reddening that corresponds to the ideal viewing geometry of the magnetic field when you have a magnetic field in the plane of the sky. But what these Planck data were saying was, no, that envelope has been underestimated potentially significantly. And that the stars in this region of sky should be polarized above that envelope. So I said, well, okay, let's go test this out. So I collaborated with the RoboPol collaboration at the University of Crete. So we got to polarization of 22 stars in the R band. And indeed, we found that the polarization was at least as high as predicted by this extrapolation of this linear fit, and completely broke this classical envelope. So we've been significantly underestimating the intrinsic polarizing efficiency of interstellar grains for the last 50 years or so. It really can't be that high. So that really gave us a lot of confidence that these regions of sky where 20+% polarization fraction, we're not only real and not some data artifact or something like that, but also we're really just the tail end of this distribution. That it wasn't something where there was something strange astrophysically going on. It was really just this evidently corresponds to just the ideal viewing geometry. So very, very gratifying to see that work out.
We have a paradigm shift.
Yeah, exactly. So I don't know if that leads us into figure 13 or not.
Maybe start with figure 12 and then figure 13 sort of summarizes the results of figure 12.
Yeah, exactly. So I had the numbering wrong in my head. So let's start at number 12. Okay, so on the y-axis here, what we have is this characteristic ratio of the submillimeter polarized intensity as measured by the Planck satellite at 850 microns, 353 gigahertz, per the V-band stellar polarization get from these stellar polarization surveys. And so in this green hashed region, we see what the value was done by the Planck collaboration over the full sky, or at least the full sky where we have stellar polarization measurements. So it was about, I think it was a sample of about 1,500 stars, maybe preferentially located in the galactic caps.
Okay.
And then in the blue, just to finish up on the observations here, is the paper from Gina Panopoulou, me, Raphael Skalidis, and other collaborators from 2019, where we did this study in just this one tiny region of the sky where the polarization fraction was extremely high. And so it was interesting that we derived a little bit different characteristic ratio here. So it's a little bit unclear as to why that is the case. I mean, there's always a little bit of trickiness when you're comparing, pencil beam observations to stars to, 5 arc-minute beams of the Planck satellite. So potentially something there. And we're also just looking at one patch of the sky rather than averaging over others. But for our purposes, we will say a model is successful if it can produce this characteristic ratio anywhere between this the blue and the green hashed region. So we'll say that that's within the range of observational uncertainty as it stands right now.
Okay.
And then so on the x-axis here is we have our axial ratio of our astrodust grains. And so for every astrodust model, we can compute this characteristic ratio as long as we make an assumption on the grain temperature, which is going to affect the submillimeter emission there. And so the 3 symbols that we have plotted at each axial ratio is a different assumption on grain temperature, going from 20.5 down to 18.5 Kelvin, which kind of brackets a reasonable range of dust temperatures for dust in high galactic latitude diffuse medium. Okay, and then so you notice that we have lots of different plots here, and those are different values of the grain porosity. So going from the top left, porosity of 0, down to the bottom right, porosity of 0.5. And so the question is, can we come up with models that actually fall within this range of this characteristic ratio of submillimeter polarized emission to optical polarized extinction? And what we find is that this is actually quite discriminatory among the possible models. So in black, we've plotted models that are able to fall within this band, at least at one temperature. So you see, 1.4 oblate spheroids or up to maybe 2-to-1 oblate spheroids at porosity 0 are good. But if you go all the way up to 3-to-1 oblate spheroids, then all of a sudden you're getting too little polarized emission per unit optical extinction. So that's still the top left panel, but this symbol all the way to the right at 3, that's kind of in the exactly, that's not been shaded. So we would say that model has been ruled out. And likewise, we can do the same thing for the prolates. And then this red hashed region in the middle here is just the constraints from that previous plot, where we're saying that you have to have axial ratios extreme enough that you can produce enough starlight polarization. And so what we find is by going through this exercise for different values of porosity and temperature and axial ratios, that the model space is actually fairly well constrained. And within this fairly general framework, we can place fairly strong constraints on what the porosities and axial ratios of interstellar grains could be to accord with these observations. And so that's summarized down in figure 13, essentially collapsing this information. So for the left panel, we have, let's go down, perfect. In this left panel here, we have the space of prolate grains as a function of their porosity on the x-axis and axial ratio on the y-axis. And so we find that there's very little parameter space where viable prolate grains live, only that top little corner there. So compact, zero porous 3-to-1. So in the top left panel, you can see them there in the shaded in figure 12. So really, prolate grains coming out of the study is not particularly viable. It seems that there's a preference for grains to be oblate. So if you look at the oblate panel, there's a lot wider range of model space where we find that we can reproduce the observations.
Very nice.
Let me just stress here that the right panel, which has all this green real estate, which looks good, doesn't go beyond porosity, 0.8. And there are theorists who are, respected theorists who would tell you that, no, if you took an interstellar grain and looked at it closely, the porosity might be, 0.99 or 0.95.
Yikes.
So because there's a scenario where the grains grow by coagulating, and the coagulation process can lead to very fluffy aggregates, which certainly from a pure thinking about what might happen to grains, it's a perfectly plausible scenario. And I would not have felt that I had anything strong to say against it until we do this kind of test and ask, can fluffy grains reproduce what is observed? And the answer is no. So the grains may be porous, but not 90% porous or more. So that is something which is challenging statements that can be found in many papers, that porosities some people will like their models to have porosities of 90%, 95%.
And that doesn't quite work here. Okay, cool.
So I guess another, I'm not sure whether we want to lead now to the 10 micron prediction. So
Sure.
now that we have this scenario where there's one kind of dust that has not all of the grain material in it, but the bulk of it. So we acknowledge that there can be other populations of grains, in particular the polycyclic aromatic hydrocarbons. There have to be nanoparticles out there that are unlike these larger grains that we're talking about, but the bulk of the grain mass is in the bigger grains, and that's where the bulk of the silicate material ought to be. So we know that our grains have to reproduce the observed silicate extinction in the 10 micron feature. So that's an observed fact. And so we design our dielectric function, developed in another paper in this collection of papers, is constrained to reproduce the strength of the absorption. But now, having done that, the polarization is now a prediction.
Yes.
So we're now already forced into particular grain shapes, particular porosities, particular degrees of alignment to reproduce a starlight polarization. And now we can predict what the 10 micron feature polarization per visual band polarization has to be, as just a measure of how much polarizing dust is out there. So these models I guess the next figure would be figure 15, just shows the results of this prediction on the right there. We predict the ratio. If you can find a sight line where you can simultaneously measure the V band polarization and the 10 micron polarization, then we predict what the ratio of those two numbers is going to be. And so there's a range of allowed models here, depending upon what you think your favorite axial ratio is, what you think your preferred porosity is. But these are the only ones that are being shown here in the solid colors are the ones which survive the previous tests.
Okay.
And so they're primarily coming out here with axial ratio, with oblate shapes being preferred. Axial ratios something like 1.5 to 2 seem reasonable. And so we're predicting that the ratio of the 10 micron polarization to the peak of the peak of the optical polarization, referred to as here as P max, that number should be about 0.22. Now, the interesting thing is that while both the numerator and the denominator of this have been measured on many different sight lines, they've never both been measured on one sight line. And it's the reason being that sight lines that are good for measuring the visual polarization usually don't have enough dust on them for people to measure the 10 micron polarization, and vice versa. The sight lines with enough dust where the infrared polarimetry can be done to get the 10 micron polarization usually have so much extinction that the optical people don't want to go to the trouble of trying to measure the V-band polarization. Why would I do that in a star that's so faint? And
Right.
so, but this is something where there is a target about, there are sight lines where both these can be done. And so we're now predicting where things should fall. So Brandon is actually involved in one project that is capable of producing the visual band polarization on sight lines where the 10 micron has been measured. And there are also people who are going after sight lines where the
Other way.
where the PV has been measured, but the 10 micron polarimetry hasn't been done.
Okay.
So Brandon, do you want to say anything more about where the state of play there?
I think we're still waiting to see how it shakes out.
Okay.
So we've stuck our neck out here and we're waiting for the observers to come along with the best number, and we'll see how we do.
See how it is. Very cool. Very good. That's awesome. Very nice. Anything else we want to cover?
Well, what do you think, Brandon? I think we want to stay away from the technical details of the paper in question. Here has a lot of technical stuff in it, which is interesting and necessary for those who want to go through this exercise of calculating these things.
Lots, right.
But I think we can skim over all that for the general, the general astrophysicist who wants just the overall top line conclusions.
Yeah, I think we've done a good job at distilling the high points in here.
Yeah, very cool. Okay, this will do. I'll be excited to see what these results come out. So
let's do.
With that,
so it's a pity. Well, I guess you're going to ask where we're going to go next.
But first, before I get there, I want to thank both of you for taking the time and walking us through your very lovely APJ article. So thanks.
Thank you.
Thanks very much for giving us the opportunity.
Oh yeah, it's a great paper. Caught my eye. So yeah, let's go ahead and talk about the future. You hit on a little bit there on that last plot on people doing both measurements along two different sight lines. Are there other things that you may want to point people to in the future? So for example, I'm shooting off the top of my head here, right? We went to, they're not spherical, so we went to spheroids. And is there a more complicated grain geometry that is still tractable to be calculated, and are there
well, the calculations
coming up
that calculations can actually be done for more complicated geometries,
okay,
but they're really time consuming. And so once you enter this space of complicated shapes, it's infinite, right? So
not an elephant. So
what kind of irregular grain do you think is a reasonable representation for irregular grains? And so that's a big barrier to progressing. We have the tools where if somebody hypothesized a particular irregular shape, then I'm willing to go out and do the calculations for it if there's a plausible reason to think that that's a interesting hypothesis. But in the absence of knowing what irregular shapes to look at, I think we have to proceed by a sequence of simple shapes.
Mm-hmm.
So another simple shape that you could imagine thinking about would be, two touching spheres as something which is very different from a spheroid, but still has a lot of simplicity to it in terms of its geometry. And so that's one direction which I'm going to be pushing in the future, but that in itself is already numerically challenging to do the calculations for.
Sure. Okay. So let me then touch a little bit. You mentioned a few times that, models made over the last few decades don't quite work out. And we're kind of in the midst of a paradigm shift here. So do you think, put on your crystal ball, and do you think over the next, let's say 5 years, 10 years, that we will have a new grain model that hits many of the observations you mentioned, or you think it will take longer than that, shorter than that?
Great. Well, that is certainly what we have been hard at work on, is synthesizing something that can explain it. And so we think that we do have a grain model, and that will be our next paper coming out very shortly, that can explain the observed dust phenomenology in absorption, scattering, emission, and polarization from the ultraviolet all the way out through the radio. And we can do it in this astrodust paradigm plus pHs, as Bruce mentioned. So we think that we have something viable, but we're also, as we said, looking for ways that we can test this observationally.
Right. Very cool. Very cool. Very nice, bright future on this topic.
So there are, potentially observational approaches that could enrich our. The name of the game for making grain models is to be constrained. And so we're already finding that the Planck people, it's wonderful what they did, but they sure made our lives harder. But that's where the fun is, right?
Exactly.
When the puzzle gets more difficult because there are more constraints, then you're more likely that if you can solve it, you have more confidence that what you're talking about has some claim to be a good approximation to reality.
Right.
And Brandon has been very much involved in looking to how all the efforts that are going into improving our knowledge of the CMB can be exploited in the same way we've exploited Planck to better constrain grain models. So maybe Brandon can talk about some of those opportunities.
Yeah, I'm really excited about microwave polarimetry over the next decade or so. I mean, because it's so integral in pushing our thinking on these dust models. So I collaborate on the Atacama Cosmology Telescope, Simon's Observatory, CMBS4, Lightbird, CCAP Prime, which are all coming on at various times of the next decade, and it'll be a really big leap in sensitivity in microwave polarimetry, as well as extending the frequency coverage of over what Planck had. And I think the combination of those two things will allow us to really drill down on these polarization spectra of dust, as well as any potential variations across the sky. So I mean, everything that we've talked about so far has just been kind of like an idealized, prototypical high latitude diffuse ISM. But with the push in sensitivity, we can also really start thinking about variations too. So I think there's a very rich science that's going to be enabled by these CMB observations. Which I should also emphasize that to do the CMB science that we want to do over the next decade, going after primordial gravitational waves and all the rest of it, really need large sky areas. And so the days of just going into the one little teeny patch that's a few % of the sky that has no dust in it or as little dust as you can get away with are kind of over. So we're really talking about large surveys of 40 or 60% of the sky that are going to have great coverage of the galaxy too. So it's just going to be really phenomenal for dust and Milky Way astrophysics.
Cool. Nice. Bruce, Brandon, thank you once again.
Thank you, Frank.
Thank you so much for having us.
And that will do on this one, everyone. And I hope this made your astronomy day just a little bit better. And we'll see you on the next one. Bye-bye.
So long.